So, good evening to the students back in Bangladesh and good morning to our speaker. Welcome to the monthly webinar of MMMRN. Those who don't know, I'm just saying that the full form of MMMRN is a multi-scale mechanical modeling and research network. So this monthly webinar is intended to invite guest speakers to talk on their research, individual research, and something they have recently published, so that the students from our university can have an access to what's going on in current research field and try to make up their mind on their own research or get some ideas about that. But I can see there are some people in here from other US universities too. And thank you for joining, by the way. And thank you for your interest. So let me tell you how this talk will go. So so Metehan will start the talk, and since I'm the moderator, I would like to ask you if you have any question, just type in the chat box. Then once the talk is finished, we can go over them individually, all the questions. And later on, when we're answering, when we are having the question answer session, then you can just speak unmuting yourself. But when the talk is going on, I think that maybe you should use the chat box to ask all the questions. All right. And as you have already seen from our past talks, that this talk will be uploaded to YouTube so that you can get access to it later on. So let's get back to our speaker, Mr. Metehan Çam. So he is a PhD candidate in mechanical engineering department at Northwestern University. So we started our PhD together, and he's a very good friend of mine. His main research topic is fluid mechanics, fundamental fluid mechanics, and how the fluid behaves in solid fluid interface, especially. And he's been doing very nice works using molecular dynamics as a tool to study those physics. And recently he published a research article in Physical Review, and he's currently working on other research topics as well. His professor is Professor Seth Lichter, who is if you are a fluid mechanics guy and if you are interested into nanoscale fluid mechanics, I guess you may have already heard his name. So he's not a kind of person who would have a illustrious website to show off his skills, but if you are into the field and if you know your professors well, you will be able to know who he is. So Metehan did his undergrad from Turkey, right? It's Bilgate University, right, Metehan? Yeah. So, and after the undergrad, he directly started his PhD here. And in the undergrad, he also worked on research topic. His undergrad research topic is boundary element method, right?
Yes.
It's boundary. So basically, he's an out and out fluid mechanics guy from the start. Right now, after the PhD, he also plans to do, I don't know, he said me that he plans to go to academia. I don't know if that's still the plan.
Probably a postdoc position.
Okay, that means he'll be here in academia. So you guys, when you are finished with your undergrad, maybe by that time Metehan is a professor, and you can of course go to his group as well. So I'll not take more of your time. Let me invite our guest speaker to start his presentation. Thank you so much.
Thank you, Sura, for this great introduction. I hope everyone can hear me well. And if you have any questions, any problems, please ask me, please interrupt me. So I think he gave a perfect introduction, so I have nothing to add. And I will immediately start my presentation. So today, the title of my talk is Slip at the Liquid-Solid Interface, Reveals Soliton Propagation and Solid Partitioning. So I would like to start with the general fundamental research question we have in our research. So we are interested in how do liquid atoms move over a solid surface? It's a very generic question, a little vague, but as we go along, you will understand what exactly we are interested in. So here I put this schematic. It is kind of a side view that we zoom into a liquid-solid interface, but at the molecular scale. And we imagine that we can see the individual liquid atoms, which are these blue circles, on a surface potential, here the sinusoidal wave created by the solid. So in this case, you can think of the x direction as the direction that we have flow, and z is direction normal to the surface. So it's been known that when you go into the vicinity of the surface, the density profile of the liquid phase is not just homogeneous. So let's put the density profile on this schematic. Okay, and here, number density of the liquid phase, rho as a function of z, but I kind of rotated and put on this schematic. So when we look at this density profile, we realize that there are some regions which are relatively occupied, and there are some regions which are less occupied. So by looking at the locations of the minima in the density profile, we can first define what we call the first liquid layer, which is the liquid layer just in the vicinity of the surface potential. And then by looking at the location of the second minima, we can define the second liquid layer, and we can go on. But the question is how many liquid layers we have until we recover the bulk, which means that no matter how you go in the z direction, basically the density profile is constant. And in fact, people in general say that the fluid properties, like with your viscosity or some other properties, are also constant. So in this figure, we can realize that after the third or the fourth liquid layer, we probably get the bulk. So what we do in my research is, in today's talk, we will only focus on the first liquid layer, and we will analyze it as an isolated entity. And we're just going to do some monolayer experiments, and monolayer over a surface. But then we will, in future work, I will give you some ideas that we will also consider the second liquid layer and see how the interesting phenomena we get in the first layer persist once we get the second liquid layer. Of course, the question is, so what does it change? So the first of all, when you create a flow, these liquid layers experience different potentials, different friction forces due to the surface. That's why these layers attain different streaming velocities in the direction of flow. And secondly, once you have more than one liquid layer, it means that the liquid particles can diffuse in between these layers, and it may definitely affect the dynamics. So this is kind of the research question, but let's go on with some introductions. So one of the things that we are very interested in is particle sorting. So in this case, here we have a picture from Freshett's study at 2009, that in microscale, that we have a solution which contains different size of microscale particles of different colors. And then we have a microchip which has pillars that are located in a square lattice. And then we force the entire solution move from bottom left to upper right corner. And people realize that different size of microscale particles go in different directions. And in fact, this technology has been known as deterministic lateral displacement. Basically, different size particles are going in the different directions, so you could separate them. And then recently in 2016, people replicate a very similar phenomena in nanoscale. Basically, now we have two different size nanoscale particles here in blue and red. And the flow goes from top to bottom, and different size nanoscale particles follow different trajectories and go into different directions. And they actually show this up to particle sizes of 20 nanometers. That is kind of the smallest particle size that have been published so far, that people say that we have a deterministic lateral motion, and in a uniform flow, we can separate particles. So we kind of get these, we consider these ideas very interesting work, and we say that, what if we replicate this in the atomic scale? What if we have a surface and we have an atomic solution and we force the entire solution over the surface, and different size or different particles go in different directions? So in fact, going forward, people already analyze similar systems at different scales. For example, there is this interesting work which is published in Nature Physics in 2019, that we have these polystyrene clusters, colloidal particles. They are moving over a hexagonal tilted surface, tilted so that the cluster is moving over the surface by gravity. And the center of mass of this cluster moves in a direction different than the driving force. And this is known as directional locking. And basically the directional locking is the underlying physics behind particle separation, because different particles are locked into different trajectories, and those trajectories are different from the driving angle of F, which is the driving force. But one of the questions is, when there is particle sorting, how does the dynamics occur? How these particles are actually moving over the surface? Are they just diffusing randomly? In fact, in this paper, they show that those particles are not just randomly drifting over the surface, but in fact, there are well-defined grain boundaries that are formed in the cluster, moves the particle in a coordinated manner. So we question that, do we have these nonlinear phenomena in atomic scale? Especially today, one of the phenomena we are particularly interested in is solitons, and I will explain what they are. And a question is, can we theoretically explain for the migration direction? Because now we say that, oh, different particles go in different directions, or they don't follow the direction of force. How can we explain that? So far, there is no comprehensive theory that explains this interesting phenomena. So finally, one of the motivations kind of comes from the fluid mechanics. So as you know that in fluid mechanics, we have the no slip boundary condition, and we also have slip boundary condition, as you see in panel B on the left-hand side figure. In slip boundary condition, we say that there is a velocity difference between the liquid and the solid right at the boundary, which we name as slip velocity, and here show by U sub S. So slip velocity is an ensemble average property, and it's a fancy word of saying that it's basically an average over time and over the number of particles you have in your system. The problem is that an average property is just a scalar quantity. It cannot really give you the molecular picture. So we say that once we have a slip velocity, how do the individual atoms just near the surface move over this when there is liquid slip? For example, here I have two animations that when there is liquid slip, it could be that all these liquid atoms move in the direction of flow with a velocity same as the average slip velocity. Or it could be that, as you see in panel B, there is a coordinated hop in between the particles. And at a given time, only few atoms are moving fast while the rest is just slow. And these two molecular pictures are quite different, but the average slip velocity is the same. It cannot really differentiate them from one another. So basically, this solute partitioning and these kind of interesting molecular level mechanisms are the reason why we are interested in this problem. So let me talk about my model, if I can go. So first, I would like to talk about an atomic monolayer on a substrate, which is the first model I will be discussing today. So as you see in panel A, we work on an ideal system that we have a monolayer of Lennard-Jones atoms. Those are spherically symmetric atoms over a cubic substrate. We use cyan spheres for the solvent, magenta for the solute, and yellow for the solid atoms. And we use periodic boundary conditions in X and Y directions. In panel B, I tried to show schematically that these particles stick to the surface, but they can also diffuse. To keep them as a monolayer over the surface, we apply a repulsive potential energy barrier in the Z direction. So these particles can move in Z, but if they try to diffuse too much, then the potential energy will force them back to the surface. So we always get a single monolayer over the surface. But I want to point out that still they can move in Z within a limited region. So in panel C, we have these black dots, which indicate the equilibrium positions of these surface atoms, solid atoms, and they create a bumpy energy landscape that liquid atoms feel. So the question is that when there is liquid atoms, when there is flow, these liquid atoms actually move along the locations of lower potential energy. So for example, we show by the white dashed lines in the lower left part of that figure, and we call them low energy corridors. They tend to move over the low energy corridors. So in my study, I apply a uniform force on all liquid atoms with a magnitude of force F, and we change the direction of alpha, which is the direction of force, from 0 to 45 degrees. And I'm not going to talk about it, but actually we use slightly different force magnitudes for different values of alpha. But I don't want to get into too much detail. So let's start one of the foremost results. So we have this mixed up solution, like you see inside the black circle at the bottom left. And we force the entire solution over the substrate. And here I plot some of the trajectories from the first 5 to 10% of the simulation. So let's follow one of the blue atoms, which are actually the solvent atom we have. And as you can see from the blue trajectory, the solvent atom goes in a different direction from the driving force F. And once we average over all the solvent atoms we have, of course, over the entire simulation, not only this portion, we get a solvent migration angle as 14.7 degrees. And then we have another atom in our solution, which we call solute A, which has a larger Lennard-Jones energy parameter, makes it more attractive to the surface. And it also goes in a different direction, in average 8.4 degrees, and it covers even less, it covers less distance. And finally, in our solution, we have solute B, which are the green atoms, has the largest amount of Lennard-Jones energy, and they also go in a different direction and covers even less distance. So we see that neither the solvent nor the solid atoms go in the direction of external force, and in fact, atoms that stick to the surface differently go in different directions. But I want to point out two things. First one is these trajectories are only the first 10% of the simulation. We make sure that our particles cover enough distance so that we have low error in the migration directions. And secondly, all these results here for a single value of alpha, which is equal to 27.5 degrees. So then we basically replicate all these results at different values of alpha from 0 to 45 degrees and calculated angles of center of mass migration for 3 different types of atoms we have in our solution, which we have solvent, solute A, and solute B. So in these figures, we have straight lines of the corresponding colors. they actually indicate our theoretical expectations. I'm going to talk about it in a minute. And the interesting result is that we have a very deterministic lateral behavior, and these different species of atoms really go in different directions, and they don't follow the direction of the external force. So let me talk about the theory. So to understand the theory, we first need to ask a question. So the question is, how strongly do different species of atoms feel the substrate? So on the top left figure, I kind of have a schematic for an individual hop of a solvent atom from one equilibrium location to the next. And in the middle figure, by using the same coordinate axis in the x direction, I plot the potential energy that the solvent, solute A and solute B atoms experience. And we realize that, and we get this nice average kind of sine curve. And we see that the atoms of different epsilon, different Lennard-Jones energy parameter, feel the surface at different strengths. To quantify this, we define U naught, which is basically the amplitude of the effective potential that these particles experience. And on the right-hand side table, I give you the U naught values normalized by the thermal energy kBT. And the takeaway is that these particles experience different potential amplitudes. And you will see in a minute how they affect their propagation direction. So we define theta as the atomic migration direction. And tangent theta is basically the distance covered in y with respect to that of x. And we can say that the tangent theta is probability of hop in y direction divided by probability of hop in x direction. So in our monolayer, a single atom can hop in 4 directions, in plus minus x and plus minus y directions, so that we can define the probabilities of hops as p sub plus minus x and p sub plus minus y. And we assume that these individual probabilities of hops are Boltzmann distributed. And what goes into these Boltzmann factors are the work done by the external force, but the appropriate components. For the x direction, it is f cosine alpha, and for the y direction, f sine alpha. And basically, we multiply this by lambda half, and we can remind ourselves that lambda half is the distance between the one of the substrate equilibrium positions and the midpoint. So by simplicity, we say lambda half is delta, and we normalize energies by kBT, the thermal energy, so that it's equivalent to 1. So once we get that, we made a final assumption and say that the force magnitudes are sufficiently enough for the solvent atoms to hop over the surface, which we actually make this assumption from our observations. And we get the tangent of the theta solvent, and we get the blue line in the right figure, which are in fairly good agreement with our simulation results. But the problem is that solutes stick to the surface more strongly. So the force we apply is not enough for them to hop over the surface. But for them to hop, there needs to be a collision. And we say that for the solid atoms, we can still make use of the same formula, but we need a correction. And the correction is correlated with delta U, which is basically the U naught of the solute minus U naught of the solvent. So that is the difference in between the potential amplitude that these sticky atoms experience with respect to that of solvent. And this delta U is different for the red and green solutes, so that we generate 2 different curves put on the figure, and they are also in a very good agreement with our simulation results. So, okay, so let me continue. So once actually we get the solute partitioning and we kind of theoretically explain it, we want to understand the dynamics of the atoms, how these individual atoms move over the surface. So I would like to talk about the dynamics of the monolayer. So here I have two panels that have sequence of snapshots at 4 different times. So in panel A at time t is equal to 1, all these particles at their equilibrium sites and they are just fluctuating. But from time t1 to t2, a particle can hop from one equilibrium site to the next. And now we have a double occupied equilibrium site, which we name as a kink and marked by a red triangle. And once we have a kink, we have an empty equilibrium site, which we call a vacancy and show by an open red square. And we realize that the particles inside the kinks propagate in the direction of external force in a coordinated manner, which yields that the kinks will start to propagate in the direction of external force. And these vacancies can also propagate, but for them to propagate, as you see from T3 to T4, an atom downstream, upstream of a vacancy should hop upstream. So then these kinks actually will continue to propagate until they recombine with a vacancy. And basically these kinks and vacancies are quasi-particles, which means that instead of tracking the atoms, we can also track the propagations of the kinks. And you will see that we will get very useful information from it. And we realize that in our system, numbers of kinks and vacancies are always equal, and which means that these properties are topological. So here, I would like to show you a video that I created on MATLAB from my simulation results. So on the right-hand side animation, we'll look down on the pure solvent monolayer, and the blue squares indicate the liquid atoms, and the black dots indicate the equilibrium positions of the solid atoms. And we use red markers to indicate the locations of the kinks and open red squares for the vacancies. And we basically use a femtosecond resolution and zoom into the interface and see how the particles are moving. So we realize that particles are moving in a coordinated way in the neighborhood of these red markers. And more interestingly, at a given time, only few atoms are moving very fast while the rest is slow. And in fact, we see that these few number of particles are responsible for the center of mass motion of the monolayer. To show that, we get the center of mass motion as a function of time in x and y directions by only considering the atoms inside the kinks and vacancies. Basically, we create the trajectories of the individual kinks and vacancies created in our simulation. Then we get the same data by considering all monolayer atoms at all times without referring to kinks and vacancies. And once we overlay them, we get perfect agreement, which basically says that this center of mass of the monolayer moves over the surface due to the propagation of small numbers of kinks and vacancies. To give you an idea that how these kinks look like, here I have 5 typical kink trajectories at a single value of alpha 27.5 degrees. They are sampled at different times, and I basically translate them over origin, so they don't really overlap in real time or space. And we realize that these kink trajectories really look like atomic trajectories. They are not so different. But the critical thing is, these are quasi-particles, these are waves. These are not atoms. And more interestingly, they are moving very fast. And I will quantify how fast they move. Like, to give you an idea, if the average center of mass velocity is 10 meters per second, the individual speeds of these guys are like 2,000 meters per second. They are 2 orders of magnitude faster than the center of mass. So finally, once we get these kinks, once we get these waves, we want to quantify them. We want to understand what they are, what are their wave properties. So to do that, we refer to solitons. So in case you didn't hear, Solitons are waves, nonlinear waves. They are of permanent form. They are localized within a region, and they can interact with other solitons and emerge from the collision unchanged except for a phase shift. To show that, I have an animation on the right-hand side that we have two solitons propagating in the same environment. And here we have the interaction during which you cannot really differentiate these waves from one another. But if you wait long enough, that we see that the fast king re-emerges from the collision. And two more things. We refer to speed and width of these waves to quantify them. Oh. Well, there's some background noise, but I will continue. Okay. So the question is, I refer to these solitons, but where do they come from? Actually, they come from a very famous and simple analytical model, which is known as Frankel-Kontorova model. The name is kind of frightening you, but it's basically you have a chain of point masses that are connected by a spring, and the entire chain is moving over a sign potential. That is basically the theoretical paradigm of what we have. So this, once we have this Frankel-Kontorova model, people show that we can basically convert this discrete model into a continuous equation that we get Sine-Gordon equation. Sine-Gordon equation is basically a wave equation, but you have a sine term, which creates actually this sine environment. It's basically the wave propagation, but you have a background energy landscape of sinusoidal form. And it has many solutions, but a solution that we are particularly interested in are topological solitons, which are known as kings and have the following form. And here, U describes the displacement of the particles with respect to their initial locations. And finally, this Sine-Gordon equation has a relationship in between the width of the solitons and the velocities. And basically, if the wave gets faster, its width decreases, it becomes narrower. So here, in the x-axis, I have atoms in a row, neighboring atoms, and the height of the blue data points indicate the displacements of the particles with respect to their initial positions. So in the left-hand side animation, as a king propagates from left to right, I plot the displacements of the particles with respect to their initial equilibrium positions. And we realize that particles in a coordinated manner hop from one equilibrium site to the next, which are shown by black dashed lines. And at a given time, only few atoms are displaced greatly, which defines the width of the solitons. Now you can say that, oh, the profile is fluctuating. Of course, there are fluctuations in the atomic scale, but we can easily say that the average profile is constant. So in the right-hand side animation, I basically plot the propagation of a king in a row which already has a vacancy in it. And we realize that, maybe I should go backward, there is an interaction period which happens very fast, but during that interaction, these two waves overlap and it's hard to see which one is which. But if you wait long enough, that there is the re-emergent king, which has a profile, has a form similar to the initial one. So once we get this, there's only one final thing to do, which is sample as many king trajectories as we can from our MD simulations and calculate their velocities and their widths. So in this figure, I regroup the trajectories, king trajectories, with respect to different groups based on their alpha and based on their direction of propagation, either in X or Y direction. And I sampled over 1,000 king trajectories. and I calculated their velocities. Here in the y-axis, I plot the velocity values normalized by the speed of sound. And in the x-axis, I calculate their widths, which is quantified by gamma. And the green continuous line is the prediction of the sine-Gordon equation. And the individual groups are in good agreement with the prediction of sine-Gordon equation. So with all this discussion, we realize that when there is solid partitioning, there are these kinks which are localized and topological. They possess velocity and width consistent with sine-Gordon solitons. And as I showed you from the previous slide, they maintain their profiles from an interaction with a vacancy, but only emerge with a phase delay. So that we actually realize that these atoms are not just diffusing over the surface randomly, but there are in fact well-defined kinks and vacancies that transport the atoms over the substrate. And these kinks are not some just random waves. They reveal the properties of sine-Gordon solitons. And these sine-Gordon solitons are encountered in many different applications. For example, maybe you heard of Josephson junctions we have, or wave propagation in shallow water experiments, or dislocation dynamics. So these kind of waves are already familiar in different scales, but we show at the atomic scale. And maybe most importantly, we show that solutes and solvents follow different directions, which actually creates the surface-driven separation. And we believe that that's an alternative to membrane-based technologies. Because let's say you want to purify salty water, and people use membranes. But membranes have their own problems. They are not extremely durable. You need to spend a lot of energy. You need to continuously pump the liquid to force the separation, and the membranes can rupture, or due to entropic considerations and the molecular fluctuations, actually you may also get salt molecules at the other side of the membrane. But here we say that we just let the solution flow over the surface, and without spending extra energy, different species of atoms will propagate in different directions. So, so this kind of the work I have presented so far are already published. I will also refer to the publication at the end. But I want to give some idea about the future work that I'm working on right now. So of course the question is, this is a monolayer. It's not really a liquid phase. What if we introduce two layers over the surface? Of course, now we have diffusion in the z direction, and these liquid layers will have different center of mass velocities over the substrate. And we question if, first of all, we get these interesting kinks. Do these kinks really persist when there are more liquid layers present? The long-term goal we want to say is, if we actually show this behavior as we schematically show here, we would like to say that slip at the molecular scale really occurs by soliton propagation, by this kink propagation, and they reveal the properties of well-defined waves in continuum equations. So I will actually pass this slide. We want to actually understand what's the role of diffusion between the layers. Let me not pass it actually. Now we have new mechanisms of kink creation. For example, a particle can come from the second layer to the first one, creates a vacancy, and that defect will continue to propagate until the atom diffuses back to the second layer. Or as you see in the right-hand side figure, an atom can diffuse to the bulk, and now atoms can hop in the direction of forcing, which we call vacancy propagations. So these are new mechanisms that we could see due to diffusion in between the layers. And of course, we have this very interesting solid partitioning in the monolayer, and we question, what if we have multiple liquid layers?
So before I finish, I want to talk about one of the one interesting result. So once we submit this paper, one of the referees asked us, can we separate atoms by their atomic size sigma, which is kind of their van der Waals diameter? So in that case, what we see is that here in the x-axis, we have particle size sigma, and we realize that as the particle size gets larger, but making sure that we still keep them over the surface, their U0 value increases, which means that they experience a larger potential amplitude. And based on our theory, we would say that as the particle size gets larger, their migration direction is lower. So here, I calculate the migration angle, theta, of solid atoms of different size sigma in the x-axis at a single value of alpha 27.5 degrees. And we see that at least the first half of the data shows that as the particle size gets larger, the average migration angle really decreases. And in a solution, different size atoms will go in different directions. But it seems that it's not valid for the second half of the data. So actually in this figure, I have two green curves. The dotted curve is the theory that you're already familiar with. But the dashed curve, which I'm not going to go into details, but that is another theory that we developed. And it seems that it explains the first half of the data quite well. The fundamental difference in between the previous theory and the new theory is that the new theory also considers the particle size. But of course, the questions that are remaining are, okay, I can pass this. The questions we are interested in, why do two solutes with considerably different U0 propagate in very similar directions? And why does the solute partitioning remain valid until a certain particle size? So the problems are, in our minds are, the atomic collisions and the kink dynamics, especially in the vicinity of solutes which have larger sigma, might be very different than our previous understanding. And we really do not consider the effect of the repulsive potential energy barrier to keep them as a monolayer over the surface. And finally, we need to revisit the theory, because now we have two theories. One of them doesn't seem to work for this new case, and the other one seems only for the works for the half of the data. So, but in the future, I would like to, actually, I'm already working with different types of molecules. For example, in the conferences, people ask me, what if we have polar molecules, like water molecules, or different types of substrates? What if instead of using a simple cubical substrate, you use a graphene surface and hexagonal pattern? Or what if you use a different coverage parameters, different densities over the substrate? So the conclusions are, basically, today I talk about an atomic monolayer driven over a substrate. And in the future, we want to keep adding subsequent liquid layers. We believe that, we agree that this is a very ideal, a very constrained system, and a very first order approximation for the first liquid layer of an interface. But the reason that we work on this system is to analyze these interesting properties as isolated as possible and see how they persist once we make our model more similar to a realistic liquid-solid interface. So in the future, especially, I would like to work with molecules with charge and dipole moments, basically not polar, basically polar molecules, molecules that are not spherically symmetric. And we believe that this is basically a new method of chemical separation at the atomic scale. And of course, the engineering application is separation over the surface, efficient separation of particles over the surface without spending extra energy. So this work actually has been already published in Physical Review E as a letter. As you may be familiar, Physical Review has many journals. E is for nonlinear dynamics, soft matter, fluid mechanics stuff. It published as a letter, so it's like 6 pages. I can also put the link in the chat if you want to see more details, and I'm happy to answer any questions. Thank you very much for listening.
Thank you, Metehan, for your interesting talk. So I'd just like to see. I've got one question.
So before that, let me put the I put the link of the paper on the chat.
I guess you have an author's copy to distribute, right? So if you could just send me the paper PDF, because sometimes, you know, it's hard to get access to the paper.
Oh, let me put that too. Yeah. Oh, that is true. I forget that completely. Give me a minute, so I will.
Yeah, you can do it after the talk. I mean, after we have ended as well. So, so one of the question I have a few. One question is that what software you have used to model the experiment?
Okay.
Thank you for the PDF. So whoever is interested in the PDF, it's in the chat box. All right.
Yes. Okay. Now, yeah.
So first question, what software have you used to model?
NAMD. I'm using NAMD, not LAMS. I know that LAMS is more popular, but we are using NAMD for.
So that's the VMD. So that's from VMD, right? That's a part of the VMD program, right?
For example, the figures on A and B. Oh, can you see it?
Yeah, I can see the figures.
Those are from VMD. Yes.
Yes.
I'm using a render. I forget the name.
Okay.
Yeah.
So next question is, did you make the atoms stay in a monolayer only by applying force on them, or have you changed the interaction potential as well?
So good question. I don't change the interaction potential of the liquid atoms with the solid atoms, but there is another potential to keep them over the surface. Basically, that potential applies an external force on the atoms in the z direction, which is independent from the interaction between the liquid and the solid. So you can think of this way: when I'm close to the equilibrium height, I'm mostly 99.9% of my interaction comes from the solid surface. But if I start to fly in z direction, then I get away from the surface, and I will start to diffuse. Then I will apply a force in the z direction to push them back to the monolayer. So this is actually a first order approximation to a very hydrophilic surface. So as you know that when we have a hydrophilic liquid, a liquid on a hydrophilic surface, the liquid wets the entire surface. So we have a fully occupied first layer. But the particles can still diffuse in z direction. What we assume that, let's say a particle diffuses from the first liquid layer. That vacancy is immediately filled by another particle coming from the bulk. And that happens instantly. That is the first order approximation. That's technically a monolayer.
So when means that the particles stay on the surface because of the liquid-liquid interaction?
The particles stay on the surface because of three different interactions: liquid-solid, liquid-liquid, and the repulsive energy barrier.
All right. And second is, well, last question is from this guy's. What force field did you use to model the solid-liquid interaction?
So, what is the simplest potential at the molecular scale? Lennard-Jones, spherically symmetric, and almost every potential for any type of liquid or solid at the molecular scale has Lennard-Jones terms in them. So I only consider Lennard-Jones, which has two parameters, epsilon and sigma. Epsilon is basically the energy parameter that kind of tells us how sticky those particles with respect to one another. And sigma is the van der Waals size, kind of the size of these spheres. But
Yeah.
for example, if someone wants to model water, then besides the Lennard-Jones interactions, now you need to model the electrostatic interactions. And now you need to make sure that your particles are not spherically symmetric, they are polar because of the partial charges in water molecules. But in my study, since this kind of work has not been done at the atomic scale, we start with the simplest possible molecular structure and molecular potential fields, and then try to work with more complicated materials.
So all these questions were from Abrar. So
thank you, Abrar.
Yeah, Ahnaf asking, is it possible to model this phenomenon with DFT formulation with a similar structure to zoom in for more insight? So basically, do you need the electron structure resolution to model this?
I think it's an excellent question. I think there needs to be something in between. So I'm doing molecular dynamics, but for spherically symmetric uncharged molecules, like argon molecules, or not quite true, but methane. But argon is more fine, neon, argon, xenon. So if I replicate the same experiments with polar molecules, which have some electrostatic interactions, and see that I have this interesting phenomena like solid partitioning or soliton propagation, but I realize that they are different from what I see here, then I will say that, oh, it seems that the electrostatic interactions matter. So then, to get more data, I could refer to density functional theory, analyze the distribution of the electrons in between the individual atoms, and see how that interaction affects the interesting phenomena we have. I mean, this is pure speculation, but I like speculations because that is kind of the first way of going in science. You first speculate and then you do some interesting stuff, you do science. So this soliton propagation are basically collisions in between two molecules, molecular interactions. So maybe for water molecules, the locations of the partial charges during the collision will really matter. And maybe depending on those relative locations, we will get propagating solitons or not propagating solitons. And if I want to see why does that happen, I would probably refer to DFT. But right now, when I consider the model as it is, I don't see an immediate necessity to refer to density functional theory. As you said that we need DFT when we want to get more information about the electronic structure, especially for polar molecules, molecules with partial charges, and the molecules that interact electronically.
Okay, thank you, Anaf, for a question. So Riaz is asking, so you have referred to using Lennard-Jones potential, but from diagrams, it seems it's sinusoidal. So are you taking superposition of the potential which appears sinusoidal?
Oh, this is, I have to say, very, very good question. Oh, thank you very much. So if I look at the figure in C, this is a surface figure. I actually made a trick. I kept the Z position constant. And this is not even sinusoidal. So at a fixed height, the potential is not sinusoidal. And the other problem is that the height is not constant. So the surface creates a very complicated potential energy that the fluid atoms experience in 3 dimensions. It has nothing to do with sin at this point. But what we say is that when the atoms are moving over the surface, there is a mean motion. And then what we do along that path in 3 dimensions, people sometimes call it adiabatic trajectory. I will explain the physical meaning. They calculate the potential along that adiabatic trajectory. And that potential actually looks like sinusoidal, like you see here. Is it perfectly sinusoidal? The answer is no. it is close to sign. It probably, I actually never did this calculation perfectly, but probably if you do a Fourier analysis on that potential energy, the first order approximation will be a pure sine, a sine with a wavelength of lambda, which is the substrate lattice constant. Another reason that we try to keep things, that we try to approximate things as sine is that we refer to Frankel-Kontorova model. And in the Frankel-Kontorova model, the background potential is sine. That's why if we want to compare our molecular dynamic results with the theoretical approximations, we need to define an effective U-naught, which is the amplitude of the sine wave. That's why what we do is we have this very complicated potential in molecular scale. We convert this to a sine. We find its amplitude, and then we insert that amplitude into the theoretical model, get the theoretical results, and compare them with our experimental results. Basically, the figure here. That figure, we cannot create it without a sine approximation because we need the amplitude of the potential. Or, for example, that amplitude actually also appears on the direction of propagation. So it's an excellent question, actually. That transition from Lennard-Jones to sine and the fact that we have U-naught is very important because that U-naught appears in theoretical approximations in both King propagation and solid partitioning. It really matters.
Right. Thank you so much, Riyaj, for asking that question. One thing that I would like to ask that, see, at the beginning, you showed us some experiments, right, where they had micro channels. So did you find, were you able to quite explain what happened there in terms of like similarities between experiments? I know that you have proposed one, I would say, hypothesis or it's a theory to explain what's going on in the phenomenon, but it seems that you have been using very simplified potential, right, LJ, and there are some other assumptions going on in there as well. But have your results at least qualitatively matched with the experiments?
Yeah, that's a fairly good question, to be honest. Okay, so actually, I will first emphasize something. We refer to these microscale experiments, but why do these particles go in different directions? They are not atoms. They are going into different directions because of the hydrostatic interactions. Because basically, in this work, people are solving Stokes flow. As you are familiar with, Stokes flow is basically the low Reynolds number version of Navier-Stokes. So then they do a similar approximation, they do a similar analysis at nanoscale. And I can tell you that probably Stokes flow also works here. Okay. But in these studies, they say that the particles go in different directions because of the hydrostatic interactions. What we say is, we actually get the idea from these studies, kind of the picture of it, as it is, the literal picture. But we say that in the atomic scale, we force the solution over the surface. Why these atoms would go into different directions? Because of the molecular interactions. That is exactly what we show. So that's why it wouldn't be correct for me to compare my results exactly with these studies.
Right.
So the thing is, but I need to compare my results. I need to experimentally validate them. So kind of that is the challenge we have right now. So the phenomena I'm referring to here is already known as directional locking at micro and nanoscale. And people compare their results with one another. But there hasn't been any directional locking at atomic scale. Right. Basically, we show it by molecular dynamics and try to explain it theoretically. When we submit the paper, one of the referees said that actually we could replicate these results experimentally. It is not very easy, but not exactly in the atomic scale, but basically by using non-dimensionalizations. by working on micro scale or nanoscale systems, maybe by using AFM, but not exactly at the molecular scale, but with the same non-dimensional parameters.
Right. So yeah, that was my idea too. So you
That
could
would be very interesting. That would be very interesting. And I'm not an experimentalist. I really don't know what would be the challenges or something.
All right. I guess, yeah. So that also came to my mind that we could use dimensional study to at least get a comparison in the pattern of the flow. All right, that's for the future research, right?
Actually, now I see that. Actually, I see that it's quite possible. What I think, and would be very interested in. I need to talk to someone, an experimentalist, rather than a computational guy like me, because I have no idea about.
Right. So, sure. I mean, it seems that you'll be keeping working on this project in the future. Anyway, we have reached the end of our today's discussion. It's 1 hour. I don't know how this 1 hour passed so quickly because I guess we're enjoying the talk too much and did not notice how quickly the time passed by. Thank you so much, Metehan, for taking out the time from your busy schedule. I know it's a long weekend. In fact, it's the Thanksgiving weekend, and you came to the office just for us. To give us the talk, and we are really grateful for your talk and for your dedication to do this one.
It was a great opportunity to. I assume that most of the people here are undergrads, so I particularly like to talk about my research to undergrads.
Right. Yeah, I think they have also. There are some nice questions. It seems that they have understood the project and they are listening to it very carefully. So from our group, I would like to again thank you so much for this talk. And the video of the talk will be, again, I am saying that it will be uploaded in YouTube. And if
so, actually before we end, you said that some of the people might write their questions on chat, but is there any other question? I just want to make sure that
I can see there is no question in the chat, but since this will be on the YouTube and some people may later come in and then watch it on the YouTube, so that's what I'm saying. So if you have any question later on that you think that you should have asked the speaker, just send me an email or send me an email, and then I will relay it to Metehan.
Actually, I'm also putting my email in the chat.
All right, then that's great. So just Abra, just disseminate the information, the email information, when you are uploading it to YouTube. All right.
So there will be three. Oh.
No, sure. Go ahead, Metehan.
So there will be three information. There's my email. I'm happy to answer any question. There is the PDF of the paper. I would be glad if you can take a look. If you have any questions, you can ask later. And Surav will share I think the link of the YouTube, right?
Right. Once we edit the video and everything. And of course, you can answer from our group. There is no problem if you want to use it on your personal website, Metehan. That's fine. This is not a big, there's no problem in that. You can share this video from your own channel too. All right. So thank you so much. Let's wrap it up. And thank you to the students who have joined us in here for your participation. I'll see you in the next talk, I hope. Thank you. Bye. Good night to the students and
good night. Thank you very much.
Bye.